I guess I can introduce our speaker. This should be kind of fascinating today. Our speaker is John Conrad, who's followed his childhood interest in space and spaceflight through astronautical engineering degrees at the U.S. Air Force Academy and Purdue University. He went straight into leadership in unmanned space programs for the Air Force and NASA. He's now retired, and his extensive career experiences never wandered far from technological development and application in aerospace and defense, as well as IT, energy, and security programs. So without further ado, I'll turn this over to John Conrad, our NASA Solar System Ambassador.
Yeah, you're muted, John.
That's not good.
Yeah, I don't understand this technology stuff.
Oh, you did real good yesterday. Real well yesterday.
Like mute buttons and stuff. It's good to see all of you, and I really appreciate your inviting NASA and myself to your session here. So let me see if I can share the slides and we'll get started. So how's that look?
Okay.
And I'm going to
Looks
try to
good
get
for me.
You can see all right?
That's fine.
Try to get the thumbnails out of the way there.
There.
Okay, let's see. First of all, I want to say this set of slides is provided to you courtesy of NASA. In my role as an ambassador, which may be something that you folks aren't familiar with, or at least some of you, what my job is, and JPL once a year selects some people to join the ranks. They've got us all across the country. We're a bunch of space and star and outer space enthusiasts that like to talk about what NASA's accomplished in space. And the way I look at it simply, especially to an audience like yourselves, is I try to answer the question, where are my taxpayer dollars going? I know that there's this government organization that does stuff, and I like to emphasize not just the wow factor of their space pursuits, but the applications that are actually really valuable. And so in my role as an ambassador, I talk, museums, libraries, especially astronomy clubs. And this is the first church audience I've talked to. And so I really appreciate the opportunity. So let me get on with it here. What we're going to talk about today, as it says, and I chose the title, A Hitchhiker's Guide to the Solar System, may remind you of a book by Douglas Adams. Some of you may have actually read it or heard about it. And I want to give a little bit of a disclaimer, because A Hitchhiker's Guide to the Galaxy is one that goes through many events. Many are quite humorous. And in fact, at some point, they decide that the Lord is a cat. And I want to just make sure that you understand that that's not part of my presentation here today. And in fact, I probably join with you. I'm a member of First Pres, as a matter of fact, and enjoy talking to other believers like this. At any rate, we'll get on with it, and we'll get to what I'm trying to do here on behalf of NASA, which is provide a look, if I can get my slides working here, which there they go, at what we know about the solar system, because we're going to hitchhike along on all the NASA spacecraft that have flown. And so for starters, we'll take a quick look here at the solar system. And I sense that there are a number of you that are contemporaries. So when you and I went through school, we didn't know of the solar system like this. It's an artist concept because we haven't gotten far enough out to take a selfie yet. But at any rate, what you're seeing here is a sphere that represents something that's still a theory, but it's what we believe to be the many small objects that populate the solar system. And the solar system simply means all those objects that are in the capture of the sun's gravity and therefore in orbit around the sun. And that influence goes way out, trillions of miles, literally. And the outer part of it has been named the Oort cloud, which we never learned when we were in school. We also probably didn't learn the name Kuiper belt at the time. And so I wanted to emphasize to you these distances simply by saying, here's a picture of Voyager 1, which was launched, believe it or not, 45 years ago, is still flying, is still sending back information, and is the distance record holder for spacecraft, 14.5 billion years out from Earth at this point, beyond what's called the Kuiper belt, which is a whole bunch of small objects, relatively small objects that are beyond the orbits of the planets. And that distance that it's traveled is that little blue line you see at the center there away from the sun. And so you can see that the solar system is much, much larger than that when you count in the Oort cloud. The Oort cloud and the Kuiper belt are also, you might be interested, the source of the comets. They're in very long elliptical orbits. They come in and go around the sun and go back out again. One of the short period comets is Halley's Comet, which you're familiar with. And so every 75 years or so, it comes in around the sun again, and it only comes in from the, it's a short period one that comes in from the Kuiper belt. There are many that come in from the Oort cloud. And once they've come in, they're so far away from us that we never see them again in a human lifetime. All right, so let's take a look at the more familiar part of the solar system in close to the sun. And you see the familiar planets there with the asteroid belt in between Jupiter and Mars. And so now we'll get on with it. I thought it'd be useful just to set the stage with the short history of where we came from. The science today says that the best estimate of the age of the universe is 13.8 billion years. And the best estimate of the age of our galaxy, the Milky Way, is almost that old. Many galaxies began back at the beginning when stars were first forming and have merged with others through the years, and ours is certainly one of those. Until today, it's a nice kind of a spiral galaxy, 13.5 billion years or so after it started. The solar system is much younger, but nevertheless, it's quite old, as you'll see in a minute. And like all systems of planets around stars, it started from the birth of the star, and that's known as a proplyd, a protoplanetary disk. Across space, between galaxies and especially within galaxies, are clouds of the original material. And believe it or not, the material across the universe is 99% hydrogen and helium, the two lightest elements. And those two elements are still there, and it took some time for there to be heavier elements. And those came about because when a star burns, and when it burns, it's called thermonuclear fusion, the stars create, the lighter elements create through fusion heavier elements, which sounds kind of intuitive. And they create some of the very heavy elements, but many of them are created when the stars die, because we understand now by observing all the ages as we look across the universe of star systems what the evolution is. And so all stars are born, go through a middle age, and die eventually. And when they die in a couple of ways. One is they just sort of energetically throw off the elements that created them. That's called a nova. But the ones that get into the news are the supernova. Those are the ones that are cataclysmic explosions that send off the material deep within them way out into space at unbelievable velocities. And they essentially salt with heavier elements those hydrogen and helium clouds and create the matter that forms into the next stars. and so on. So at some point, the spinning disk, because as matter contracts, these clouds contract because all the particles are heavy, massive, and they attract each other. And when something disturbs them and they come down and start to form a much more compressed gas cloud, they spin because everything's in orbit, and they spin and create disks instead of spinning spheres eventually, the protoplanetary disks. And those disks eventually have the center part go into such a state of compression that it heats up enough to start burning, and that is a star. And in the case of our sun, that happened about 4.6 billion years ago. And as this artist picture here indicates, once the star in the center, in this case the sun, lights up and starts to burn, there's still a lot of gas out there, and that gas slowly but surely collects by a process called accretion into planets in their own lanes, and eventually all the planets of any particular star system sweep out all the material in their orbits as they go around by gravitational attraction, and the star system is left with these large planets around it. So, with apologies for maybe a little too much of a science lesson there, I wanted you to know where our star system, in this case the solar system, came from. And so now we've got the planets. And here are actual pictures of each of the 8 planets now, in order, away from the sun off to the left there. And you can see that there's quite a difference between the 4 on the left and the 4 on the right. The 4 on the left, which include Earth, known as Terra, give the name to the 4, and they're known as the terrestrial planets. They're all made up of the matter that was in towards the sun, which included a lot more rocky matter than the outer planets. And so they form into hard planets as you go out there: Mercury, Venus, Earth, and Mars, which you're familiar with. And then the outer planets, which you'll see in a second, are much further out. This is not true to scale. It is true to the size scale of the planets, but it's not true to distance scale. The outer ones are gas all the way out to their surface. We believe they have a core, but we of course can't observe that easily. So the outer planets are much bigger. The ones that are furthest out beyond Jupiter and Saturn, in this case Uranus and Neptune, are very large, but they have they're so cold that they probably have an icy crust on top of their gas. So the inner 4 are different from the outer 4 in size. They're very different in distance, not just in that they're farther out, but the outer 4 are much further apart. You can see the distance of each of them there at the bottom. An AU is the distance unit, which you might guess is called an astronomical unit. And it's defined simply by the number 1 that you see there underneath Earth, which is an astronomical unit is equivalent to the distance from the Earth to the sun. And we measure everything else in shorthand by talking about how many AUs it is. And so, for example, there are 2 planets at 0.4 and 0.7 AU closer than Earth, and so on. So the pictorial here doesn't do justice to the separation, so I tried to change the scale to make it more true to distance. And you can see that the 4 terrestrial planets are bunched in there at only 1.5 AUs from the sun. You have to go 3 times or more further out to get to Jupiter, and twice as far again to get to Saturn, and twice as far again to get to Uranus, and half again as far to get to Neptune. So they're way out there. The next difference between the inner 4 and outer 4 is the number of planets, and this is probably due to the size. The larger the object, like Jupiter, the easier it can attract and hold other objects in orbit around it, and objects in orbit around a planet, of course, are moons. So the inner 4 only have a total of 3 moons. One is our moon, and the other two are much smaller moons of Mercury and Venus and Mercury, I'm sorry, of Mars. Phobos and Deimos are moons of Mars. And the other two planets, Mercury and Venus, don't have any, as opposed to the outer four, which have literally dozens each. The count has been going up steadily as our Hubble Space Telescope has been able to study these systems, and other telescopes on Earth have gotten much better. So in the last 20 years or so, we've probably doubled the count of moons, and there are many out there. And the last difference between the inner and outer four is because of that stony and rocky and hard matter that was accreted in the terrestrial planets versus not having much of that in the outer gas cloud. And so the structure of the planets is quite different in that the inner ones have a hard crust and the outer ones have a core, we believe, and a mantle is nothing more than the definition of all the material on top of the core. In the case of the gas giants, it's gas all the way out. And so that's quite a difference between the two sets of four. So now, as I promised, we're going to get on board NASA's spacecraft and take advantage of what we've learned by flying out to the planets. And believe it or not, it's over 6 decades now. And you folks are an audience that can appreciate, as I can, just how things have changed in our lifetime. Imagine, I was in middle school, which of course we didn't call it middle school then. I was in junior high when Sputnik went up, and high school and college when we finally got people up in space. And that was 64 years ago when NASA was formed in 58. And NASA was actually formed about 6 months after the first US satellite was launched by the military. So it is a 64-year story because we got busy right away with NASA spacecraft. And while we can learn a lot from Hubble, and I want to point out maybe the greatest accomplishment in terms of looking across the solar system that Hubble has had, and that came in 1994. And the picture here is actually an image taken by Hubble of Jupiter. And that stream of stuff that might look like doesn't belong on the screen in the lower right there was something called Comet Shoemaker-Levy. And you may remember in the mid-90s when this happened, we observed, and we were fortunate to have Hubble up there. It had only been operating with focused images for a year at the time. We observed one of the many comets that comes in toward the sun, and as it went by Jupiter, because of Jupiter's great attraction, it actually changed its orbit and broke it into pieces, because comets are kind of loose things. They're ice and snow and rock and dirt. And it broke it up, and we estimated that the trajectory, once it went around the sun, would come back out, and not just come back out past Jupiter, but because the orbit had been changed, impact Jupiter. So we were able to stare at it with Hubble as the pieces that it had broken into one at a time collided with Jupiter. And we were able to measure with the ultraviolet part of the spectrum the energy of the collisions and calculate that the biggest piece released probably a little more energy than the asteroid that killed the dinosaurs back 65 million years ago. And it was quite a wake-up call about near-Earth asteroids, to note that if one of our neighbors could get hit in our lifetime by something the size of what wiped out most of the species on the planet, then we ought to pay more attention to what we're going to do if one of them comes in near us. And it provided the kind of kick in the pants, which is to say, setting up an organization called the NEO office, the Near Earth Object Office. And we eventually named the Planetary Defense Officer, who works out of the NASA Planetary Defense Office in Washington, to make sure that we can do our best to identify all the big objects and figure out ways to deal with them if they come in towards Earth. So that's a little bit of an aside I thought you might be interested in. So Hubble's good at seeing things, but it's much better to send spacecraft there so you can do things up close. And so the reasons are pretty obvious. You've got much higher resolution. You can look with different instruments across the entire spectrum. You can actually, in some cases, have probes that go into the atmosphere or landers that go down to the surface and get very direct measurements. So that's a good set of things to explain why we authorize and spend all that money on spacecraft. But the deepest reasons are two, and you could probably guess them, or certainly one of them. And that is, we keep asking the question, are we alone? And so can we find life in the solar system? And so a lot of the justification for these missions came about to be looking for things that could support life, or whether it's life like us or other kinds of life. And the other big question has to do with, where did the Earth come from? How did it form? What can we learn by studying other planets to understand the evolution of the solar system, and in turn, things that have to do with our own planet and things that we can't see without certain kinds of views that we can get of other planets. So we're going to start our journey with the spacecraft at our good old sun. I just love this picture because it's such a faithful representative of what that wonderful warming thing that we see in the distance looks like more closely in terms of the visible evidence of energy and magnetism and so on.
That's the sun. I thought.
Did somebody say something? Incidentally, I'm open to questions if anybody does want to interrupt me because something isn't understood. All right, so in the first couple decades of the space age, which began in '57, we got after getting better looks at the sun. And initially, all we did was get some spacecraft up out of the atmosphere. We called them OSOs, orbiting solar observatories. NASA Goddard down near Washington was actually the center that did that. And I knew the program manager at the time because I was doing some other work for them. But at any rate, these spacecraft only went into orbit around the Earth, and they did give us the opportunity, without the atmosphere blocking it, to observe the sun and study it. But then we quickly got rockets that were powerful enough to escape Earth's gravity and go out into orbits around the sun instead of around Earth, and get better looks in order to measure things. And through the decades since then, I'll just kind of summarize in one line here, we've had half a dozen more solar observing spacecraft, which are quite, they always stay up with the state of the art of instruments and understanding. And our understanding of the sun is easily 1,000 times greater than it was before we got up into space and started studying it. And in particular, we term our understanding of it as space weather understanding, and we can actually predict it and observe it. And it has to do with all of that energetic matter, call it plasma, that can be ejected off of the sun, and those are called coronal mass ejections, and get directed wherever they get directed, out into space. And sometimes these coronal mass ejections get to Earth. They're directed towards us, and they travel at tens of millions of miles an hour. And when they hit, fortunately, we have a magnetosphere, and so that magnetic field shields us, or else we would be damaged, we human beings, and the surface would be damaged. But the energetic material gets into the Earth's magnetic field. It creates spectacular aurora. And if it's a bad coronal mass ejection, it actually wipes out some of our satellites. It just, it basically electrocutes their electronics. And whenever we have astronauts in orbit, we have to watch for these things coming towards us. And they have to actually get behind shields sometimes in order to protect themselves. Space is a pretty unfriendly place. at any rate, that's space weather. That's part of what we've learned and continue to study. And the latest probe is this one here. It's called the Parker Solar Probe. And there it is looking at the sun, although it never gets that close to it. It's just an artist's concept, named after one of the solar scientists who died recently, but was very much honored by having this probe named after him, which was launched before he'd passed away. It's midway towards becoming the closest approach to the sun that we'll ever have. It's going to get, as these elliptical red orbits on the left show, in closer and closer each time, as opposed to perigee around the Earth. It's called perihelion when you get close to the sun. And eventually, in I think 4 or 5 years, it will actually be at its closest approach, well within the solar corona, which, because it's so close to the sun, we haven't been able to study with telescopes. It's just too hard to see there. And so Parker's going in there so we can really understand what's going on really in close to the sun, only less than 10 million miles out. All right, so you might think we'll go towards the planets next, but I thought we'd actually go where NASA went next, which is our closest neighbor in space, the moon. And in '59, less than 2 years after Sputnik went up, the successful lunar probes had been launched to actually hit the moon. And there was also an orbiter. And guess who did that? Well, you folks may remember. I remember very well being in school what a flurry it caused when Sputnik was launched. And for the first time, America worried about not just where we were substantively, but the cosmetics of us versus the Cold War enemy, the USSR. And so Sputnik was a victory for them. And now they had the first successful mission to the moon. And the first wave of what today we call STEM hit. I don't know how many of you remember this, but certainly in my schools in Ohio and New Jersey, where I went to school, the science and math programs changed pretty significantly in those years in the late 50s and 60s. And I enjoyed that acceleration. But at any rate, we were worried about the Russians, who, as you can see here, seemed to be quite a bit ahead of us. Despite the fact that we hadn't gotten to the moon yet, a couple years after that, President Kennedy sort of threw down the gauntlet and said, within this decade, we're going to land on the moon with people. And we hadn't even had John Glenn orbit the Earth yet at the time. I mean, that was pretty gutsy. So we continued to try, and the Apollo program was underway. The first success that we had getting to the moon, believe it or not, didn't come till 3 years after Kennedy said that. We got there and we hit the moon finally after trying 13 times and failing before then. Once again, we were really trying hard to do what seemed to be catch up with the Russians' capabilities. The first soft landing on the moon took place. Again, this was a space race, and so it was the Russians again that got there first and landed an unmanned spacecraft on the moon in '66. And we did get there. Our program had finally picked up and we were off and running. Now, 5 years after Kennedy committed us within an 8-year period to get to the moon, we finally landed a spacecraft, unmanned, of course, on the moon, a Ranger. And we landed several of these Rangers, and they served as reconnaissance to study various lunar landing locations for people. And then we had a big success a couple of years after that, Apollo 8, which we may all remember because it was featuring 3 astronauts orbiting the moon for the first time that humans had done that, and reading from the Bible, reading from the creation story, the first 10 verses of Genesis on Christmas Eve. I do remember that one. And then finally, less than 8 months after we orbited the moon, we were able to put Aldrin and Neil Armstrong down on the surface. And it was a huge relief, among other things, because basically space was a theater of the Cold War, and we won. The scorecard is really instructive. It showed what humans can do when they decide to really focus on something. I'm not sure what we do today because we do things so much more slowly, but at any rate, an average of 6 lunar rockets a year for an 11-year period after we got started. The Russians had a few more than we did. We had a number more successes, including the first lunar landing. And believe me, it was not at all clear that we were going to land people there before them. They were trying hard, and we actually launched that Apollo 8 that had Borman and a couple other astronauts go around the moon a little bit early, because our intelligence had told us that they were about to send people up there and we wanted to beat them with something. So it was quite a Cold War race. And of course, we didn't stop at that point, but we won that particular set of battles, if you will. The next thing we were going to do in parallel, starting a little later, was get after our nearest neighbors. And the nearest neighbor is Venus. And here's as good a picture as you can get today of Venus. This is a Hubble picture. And the reason it looks like that is because Venus, it turns out, has such a thick envelope of gas that you can't see through it. And it is true to what is shown here, very slightly smaller than the Earth. And it was the first planet that we went after. And as you can imagine, once again, we had the situation where the first people that had a flyby were the Russians. Within about 3 years of Sputnik, they got a spacecraft out there. It turned out it didn't do very much. We actually got one there a year later. Ours had instrumentation on board and was able to make some useful measurements of Venus. The terminology is important to understand, you may know, but we're not talking about landings. We're not talking about probes that go down to the surface and impact it. We're not talking about orbiters. We're talking about spacecraft that have a trajectory that takes them close, and they fly by and don't come back. So we get one set of views, obviously, of pretty much only one side of the planet that we go by, but it is a way to get up close to it, and so flybys have been very valuable. The first soft landing on Venus finally was achieved, and the first unmanned spacecraft landing safely on another planet took place in '67, and again, that was the Russians. We did have lots of successes against Venus. We really got into the program by the '70s and had a number of Venus spacecraft over a 20-year period. You don't see any mention there of landers. We've never landed a spacecraft on Venus, not because we couldn't, but because we've decided we don't need to, or it wouldn't be useful at this point. We have had a number of mapping spacecraft that have orbited for years and used radar, which can penetrate through the atmosphere. And so if you look at that fuzzy image, when you spend years orbiting it, you get a much clearer view of the surface. We've mapped the surface of Venus very nicely, and we understand it quite well, and it's a really forbidding place. The Russians, for their part, decided that they did want to have landers. So not only the first one in '67, but they had 4 more here, 2 in each year, and another one, the very last spacecraft to land on Venus was in '85. It was again a Russian one. And the reason that we didn't do it is simply it's so hot. It's almost 900 degrees on the surface of Venus. We estimate, based on all of our measurements, that it was roughly 2.5 billion years ago when they had a runaway greenhouse effect. this atmosphere that's some 80 times thicker than Earth's atmosphere is almost entirely carbon dioxide, which of course is a greenhouse gas, and the one that we're worried about now, along with methane, is the ones that have intensified global warming. And so global warming to the nth degree is what Venus suffered 2.5 billion years ago. 900 degrees can melt lead on the surface. The atmosphere is so noxious because it also has sulfuric acid in it. And so the Russian spacecraft, none of them lasted more than minutes when it was on the surface, and seeing through the haze was not possible. So you don't get much value. And one of these days, we may do meaningful science on the surface, but what the US has done is orbited and looked through the atmosphere. So the next neighbor, which we went after in parallel to Venus, is Mars. And this is a faithful representation of the size of Mars versus Earth, much smaller. The Russians weren't successful here. In their first decade, they failed with every one of their 9 attempts. We had some good successes. Mariner 4 flew by and took the first close-up photos of any planet in '64. We had more flybys, and then we finally orbited with Mariner 9 in 1971 and got some useful value out of that. And then finally, and not just orbiters, but the first soft landing was done with an unmanned spacecraft on Mars in '71, and that was the Russians again. The space race was still on. We did decide to make it a centerpiece of our bicentennial celebrations in '76. People like me that paid attention to the space program noted all this, and Vikings 1 and 2 were launched, and they both orbited and put landers down on the surface. And we had more useful spacecraft through the next decade or two. But the next really notable thing was when we had a lander that also had a little rover that drove off of it when it landed softly on the surface, and that was Sojourner. And you may or may not remember, but it got in the news a lot. It looked to me like kind of like a folded up card table with casters underneath it, with a couple instruments on top, but nonetheless, it was the first mobile lander on a planet. So it went around and studied some rocks and things, and was pretty exciting. And since then, we've had lots and lots of activity at Mars and lots of success that we'll look at quickly here in a minute. But I wanted to kind of summarize what happened in those first 20 years, roughly, of the space age, going against our 2 nearest neighbors. First Venus, and shortly thereafter, we went after Mars. We did a lot of it through the '70s, and then things changed and priorities changed. And basically, it went back to the one of the 2 major things that justified programs, and that was this search for life, or at least water. And we decided that Venus was not the place we wanted to go look for this sort of thing. And so we pretty much shifted our budgets to go after Mars, which is the place that shows the most promise still. A very interesting and useful and busy slide that NASA provided to us that I really love. If you start at about 12:30 here on the clock, you'll see a spacecraft that was launched in 1960, and the red flag there with the little tiny hammer and sickle is for the USSR. And so if you go around clockwise, you see all the different spacecraft that have been launched towards Mars in the last, roughly in the first 50 years of doing this, up to 2011, which was the date of when they produced this slide. And so we're not going to dwell on this, except I thought I'd just kind of summarize what happened. In the first 2 decades, you see only Russian and US flags there on these missions, and there were quite a few of them. As this simple to understand code indicates, while they were all launched, The red X's mean they did not achieve mission success, and the green check marks means they did. And so most of them were failures. Another 20 years, and you might think that the next couple decades would lead to a lot more success with better technology. It turns out there were even fewer successes in the 80s and 90s. And finally, since the year 2000, we finally did get much more effective and successful with our missions. And so to kind of summarize, NASA gave us this little scorecard of all these missions over the first 51 years of sending missions towards Mars. And the score was Earth 16 and the Mars Imperial Defense Grid 22. So the NASA scientists and engineers, among other things, have a sense of humor. At any rate, I thought it was interesting to add to this slide by crossing out everything that wasn't a US mission to show what the US did in that time period. And so here we show that of the 16 successes, 14 of them were ours. And most of the failures were another country, usually Russia, but also the Japanese and others tried it too. So we had about a 75% success rate in those years up to 2011. And there have been a couple more successes with InSight, a lander that's doing seismic measurements on the surface. A few years back that landed. And just over a year ago, the latest rover landed. That's the Perseverance rover that you've probably heard about in the news. And so our current rate is not 14, but 16 successes against 5 failures. So we're pretty successful, I'd have to say, against the Mars objectives that we've had. You see across the face of Mars there, since the year, actually starting with Viking back in the bicentennial year, but the rest of them are rovers, including the various latest ones and the Phoenix lander. So lots of activity up there. And out of all that, NASA gave us this slide to sort of summarize their finding. So I'll just let you digest that. Again, NASA's got a sense of humor. So that's the most activity of any JPL, especially spacecraft on behalf of NASA that have been done through the years. So what about our other interterrestrial planet? You might be surprised that we didn't actually get there and study it until 2004. And the reason why we waited is quite interesting. It's not just because it wasn't our immediate neighbor like Venus and Mars. It's because due to an understanding of rocket science, orbital mechanics, and propulsion, you can calculate that when you put yourself into a trajectory that goes into the great attractor, which is the sun in our system, and to get to Mercury, you go in closer to the sun. Once you get in near Mercury, you're going much faster. And in order to go into orbit, I mean, you can go in there with the same amount of fuel, for example, that you do towards Venus, which is also in towards the sun. The first hard step is escaping Earth's gravity. But once you get in towards Mercury, 2/3 of the way in, you have so much energy being pulled by the sun that you have to carry along a lot of fuel to slow down to go into orbit. Turns out it costs you more fuel to launch and get there than it does to escape the solar system entirely. So we put it off for quite a while. NASA Messenger launched in 2004 was when we finally decided to expend the funds and the rocket fuel and so on to go into orbit there. And it orbited once it arrived in 2008 for 7 years. It mapped all of Mercury, as you can see. It looks a lot like the moon. No atmosphere, fairly small body, and subject to all the asteroids and comets that might impact it. And so it has a surface that looks a lot like the moon's. We mapped it in detail. We understand its atmosphere or lack thereof and its magnetic field. One thing I thought I'd mention is quite interesting. Mercury, without an atmosphere, as it rotates like Earth does and turns a day and a night phase alternately back and forth, has a very wide and very extreme temperature range, both on the day side, which is extremely hot, and the night side, where all of that heat radiates off into space without any atmosphere. And so that's the extremes of Mercury's surface temperature. But interestingly, there are near the poles, and this is true on the moon as well, craters with deep floors where no sun's rays ever hit in the 4.5 billion years of the planet's life, or whatever is the age of the craters actually, which is billions of years. There's never been any heating of the floor of these craters, and so we find water ice in there despite that temperature range. All right, so on to the outer planets. And here is a very quick look to summarize, going to the gas giants, Jupiter, Saturn, Uranus, and Neptune. Pioneers, 2 of them, and Voyagers, each successfully and successively with their 1970s launches went by Jupiter and got us better and better looks at Jupiter. Again, just flybys. A couple of them, Pioneer 11 and Voyager 1, had calculated trajectories to fly by and then head for Saturn and fly by there. And the Grand Voyager 2 interplanetary tour went by also as designed. The trajectory was designed to go by Uranus 5 years after Saturn and Neptune 3 years later. And these are going, 40,000 miles an hour or so. So it takes years to get between these planets at those speeds. The first of the great big orbiting spacecraft to the planets was Galileo. And Galileo was launched in '89. You can see that it's 15 or more feet tall there in proportion to the people standing underneath it in the lab. And you may see that there's this red domed piece right next to the people. That's a probe. And so when Galileo launched in '89, arrived in '95 at Jupiter and went into orbit for 8 years, it dropped a probe into the outer envelope of Jupiter, which, as I said, was all gas. And so that probe was instrumented and had communication system to send back measurements of the outer envelope of Jupiter. And those were such useful and interesting measurements, but also ambiguous, so that we have some mysteries that we're still trying to solve from the data that we got in 1995 from that probe. The next huge, and in this case about 20-foot tall spacecraft was Cassini, and it was designed and launched towards Saturn and had what I would have to say was probably the most valuable overall interplanetary mission of NASA's. It ended in 2017 after the orbiter, which arrived after a 7-year voyage in 2004, spent 13 years orbiting Saturn. And as it orbited Saturn with its many moons, the orbit was changed over and over again to observe the rings in different ways, and about a dozen of the moons with many, many passes, especially the moon Titan. Titan, I'm just going to pause and note, because most people don't know this, it's the most, if you will, planetary-like moon. Not only is it large, it's the second largest moon in the solar system after Ganymede, and it's much bigger than our moon, but it has an atmosphere, quite a thick atmosphere, so thick that we think if we took the wings that we've seen some people try flying with, maybe back in the 1800s, jumping off cliffs, on Titan, it turns out the atmosphere is thick enough that a person has enough power that they could probably fly on Titan. Titan Also has the feature that it's the only body in the solar system that has a liquid that can exist in all three states on the surface. In the moon, the Earth has that with water, good old H2O. And on Titan, it turns out it's methane. It's about 350 degrees colder way out there, but methane exists in its liquid and vapor and solid state at those temperatures. And in fact, what we find on Titan is mountains and river valleys and creek beds and lakes and things like that that are filled with methane when it's in its liquid state, which evaporates off into clouds of methane and rains out and flows through the topography and freezes at the poles and so on. So it's in some ways quite an Earth-like body, unique. The reason we know this is partly from that orbiter that over and over again used its radar to pass close to Titan and take images of it, I think well over 25 times, but it's mostly in the details due to Huygens. Huygens is the name of the European Space Agency probe that you see in that little, if you will, cartoon there at the top, going towards Titan. And that probe was well instrumented with imagers and other measurements so that under a parachute, as it floated for more than an hour down to the surface of Titan, we got to take a look at these mountains up close and the plains and the rocks and so on before it touched down, and sent back data for well over an hour after it landed. So the Europeans, Huygens, joined the NASA Cassini, and it was a really successful spacecraft mission. So next we head out to Pluto. Pluto is a very interesting place, much smaller than the other planets. When New Horizons, the NASA mission towards Pluto, launched in 2006, Pluto was still officially a planet, just like when we went to school. And about a year later, while it was on its way, the International Astronomical Union, in their deep wisdom, despite cheerleaders to the contrary, decided to demote Pluto to a dwarf planet, like about a half a dozen other similarly sized objects, one in the asteroid belt and the rest of them out in the Kuiper belt with Pluto. So nonetheless, whatever it is, and I have to remind people that these labels are not provided by the creator. They're provided by man. So we just look at nature and discover things and decide what labels to attach to it. And Pluto's latest label is a dwarf planet, despite the truly religious fervor of people that want it to be a planet again. The mission is still going on, as the plus sign indicates, launched in 2006. In 2015, it got there, took images like the one you see there that are just spectacular, and taught us things that said that Pluto was a completely different kind of a cold, distant body than we'd expected. It has active geology. We estimate that it's got cryovolcanoes, whatever they are, and topography that's quite a bit more complex and exciting than we had anticipated. As New Horizons continued to fly out there, we targeted what's known as a Kuiper Belt object, a KBO, and it went on to that. And about 2 years ago, I think, or maybe 3, on January 1st, it had its close approach to this KBO, which we named Arrokoth, and it's what's called a binary. Two objects whose mass causes them to attract each other and orbit around each other. In the case of Arrokoth, we believe, but we're not sure because we didn't get the perspective all around as we flew by, but we believe it's what's called a contact binary. So it's not really hard attached. And you may or may not know, many of the larger asteroids are nothing more than smaller asteroids whose mutual gravitational attraction caused them to pull together into larger objects. and we sometimes refer to them as rubble piles. They look big from a distance, but if you hit them hard with something, they break into pieces. So that was Pluto. We got there in 2015. The other NASA planetary mission that is still ongoing is called Juno. Another mission to Galileo, since the technology that was available on Galileo in 1989 when it was launched, when we might have still had our Commodore computers and very little memory, was what was Galileo's capability. Juno has the 2011 technology that arrived at Jupiter in 2016. It's been there for 5 years, and it's given us tremendous insights, partly because it's a very different orbit than other spacecraft have taken. By design, it went over the poles, and it's now in orbit flying over the poles of of Jupiter, giving us very different views than we're used to seeing. So at this point, I wanted to give you an opportunity to ask me to either stop or give you another 15 or 20 minutes. I can stop quite quickly if you'd like me to and just summarize. So I'll leave it up to you, Ted or Dave. What do you think?
I think if anybody has a question, this might be a good time to ask, and then let John continue.
Yes, John, looking at the distant planets, I didn't see anything about the planet Uranus.
My summary slide notes that our robots haven't gotten to Uranus or Neptune yet. We had a flyby back in I guess it was in the 80s of each of them, but that's as close as we've gotten. One pass, some up close pictures, and that's it.
John, a couple of questions.
Sure.
Number one, is any of this going to be on the final? And second, about, I don't know, 15 years ago, I sat in on a NASA budget meeting of the House Space Technology Committee, and the bureaucrats that were testifying were going on and on about the budget. And the congressman sort of hand waved it all away, and they wanted to know what are the practical applications of what NASA's been doing. So could you go over some of those?
Other than Tang?
Yeah, that.
I worked in the government, excuse me, briefly as a civil servant in the mid-70s in the energy program, because I thought it was an exciting place, given the fact that there were long lines at gas stations, and all of a sudden solar and wind and fusion and all those things were coming. So I went and worked at something called ERDA, the Energy Research and Development Administration, which was sort of that short piece of time between all the different energy agencies like the coal, the coal people and so on, and DOE. And I was there for 18 months. And the way I would summarize that is I realized as a civil servant that I was too young to die at the age of 30. So I got out and went into industry. But my point here is that I had the opportunity then to look hard at practical applications of government programs, because we had stuff circulated every day that was trying to convince us of that. And so I'm very sensitive to your question, because that is a really important question. But I'm going to bail out a little bit and say it's an extremely hard question to answer. The fact is that there is no question that many of the world's best space scientists of all kinds, whether they're paleoscientists looking at ice cores in Greenland so that we can ground truth stuff as we do our passes over Greenland from space, and give us anchor points for the calculations that we do about the ice mass melting not just where the glacier tongues are, and we can see it easily. My point, and I could probably give you a dozen examples, is the things that space provides to us are synoptic views, overviews of things that we could never get otherwise. For example, global warming. You know, my favorite talk to give, if you'd ever like to have me come back and give it, is called Global Climate Change. I emphasize that global has to be in there, not an American problem. It's certainly not a political problem. It's a mankind problem. The View from Space, that's the name of the talk. And my point is that maybe for a couple centuries of the Industrial Revolution, we could observe this and that thing and eventually put buoys in the ocean or gather enough comparable data across enough places to be worried about things, but without the overview of down-looking spacecraft to understand what was actually going on globally with all of the parameters that allow us to understand what's happening. We never could have fully understood in a broad sense or had the data to feed the models to really understand how firmly climate change is desperately a desperately bad problem for Earth. At any rate, the similar thing, and so it's the contribution of Earth-looking spacecraft in that case that sort of turned the trick over the last 30 years, especially as we've been able to monitor the ice packs and the sea levels and so on. Benefit to mankind, immeasurable in terms of that sort of thing. As far as the visits to other planets, we will only be able to tell in terms of the search for life, especially as it goes on with Perseverance rover in the Jezero crater on Mars, as it looks for microbes to be evidence of whether there was life associated with the delta and the lake that it's now driving around in. And that will give us some more information. How valuable is that? I guess that can somewhat be answered only in a very personal sense by how valuable is it to understand whether or not there's other life on nearby planets, let alone in the universe. But the actual value of space technology is broadly useful, like most areas that have had R&D budgets, in how it sort of, like a rising tide, pulls along other things. I mean, I did work for much of my career serving the Defense Department and serving parts of it. You know, I was actually involved in and did launch some of the early down-looking spy satellites, which I couldn't say until the 90s when that was fully unclassified. Did that have benefit to mankind? Certainly it did, in terms of Eisenhower first and then Kennedy and others later being able to confirm or deny things that weren't talked about openly before they decided what steps to take in the international security community. I really apologize. You've asked an open-ended question. It's one that doesn't have, here are the top 10 transferable technologies. I've looked for that myself. I can give you the web address that you can have and share with the others if you wish to. I'll look it up after the meeting because NASA does have a tech transfer office, and they can, you can actually look at their, I think their weekly newsletters or maybe monthly newsletters. If you want, I can provide you that to give you more specific answers. But my answer after a career in it is very hard to answer specifically because most of the value in these things has to do with how they work in tandem with other developments. Not a great answer. I apologize for that.
John, I think if you send the web link to me, and I'll get it over to Dave, and he can send it out to the group distribution list.
All right, Ted. I apologize. I can't give you the quick list.
Yeah, no, that's okay.
John, I have an easy question for you.
Sure.
John, this is John Spellman, your old dentist.
Oh, no. Hello, John. How are you?
I've been taking a close look at you this whole past hour, by the way.
I'm gonna use my skills with Zoom here and flip through the thumbnails and see if I can find you here.
Yeah, I'm waving right here. But anyway, on a little different topic, I just wanted to know if your family's still involved in supporting American natives.
That's a great question, and I really appreciate that. Janet isn't here at the moment, but yes, the organization she founded in '97, 25th year now, Naftali, well supported through the years, and I don't say this for any other reason than it's true by our home church, First Pres. That's not to, set a marker out there or anything, but at any rate, yeah, it's got still growing support, 25 years in, serving the Lakota Indians in South Dakota.
Well, maybe she can be a speaker to our group in sometime in the future. That would be a nice talk.
I will pass that on to her, John. I really appreciate the question. Thanks.
Great.
I have a question. This is Dave Goodale. What does NASA?
We lost your audio, Dave.
Dave, you're muted, I think.
No. Take down the hands up icon, Dave. We can't hear you.
Nope. Can you hear me, Dave?
Yes, I can. Now we can hear you, Dave.
Okay, there we go. Question?
My question was, what has NASA learned about the origins of gravity or the mechanism of gravity?
Have you heard of LIGO? LIGO is I believe it's laser interferometry, gravitational observatory, something like that. At any rate, LIGO is an incredibly creative idea of how to actually look for gravity waves, which were predicted by Einstein over 100 years ago. And it had its first success, I'm going to say about 10 years ago. And now it's had a number of successes. But at any rate, we have confirmed, and that's with, and I'm going to really show my ignorance here and say that I believe LIGO is, I'm going to tell you, I don't know whether it's actually a space-based platform. I know there is one, whether LIGO is it or whether it's a ground-based platform. But the answer is NASA's been very much involved in looking for gravity waves, and part of that development of that instrument and part of the success of finding them. As far as understanding what gravity is, it's one of the great mysteries, and there is no clear understanding of that yet. It's one of what are called the four universal forces, the others being the strong and weak nuclear force and electromagnetism. And gravity is unique in that it operates at a distance unlike any other force across the universe. But it's also the weakest of the forces in a sense. So I'm kind of exhausting my understanding of these kinds of things here.
Well, John, I understand.
But there's no clear answer to what it is.
I understand Legos. I play with those all the time. How do you spell LIGO?
LIGO, all caps.
Okay.
You can Google that and read all about it.
Thank you.
Mm-hmm.
John, I just want to say thank you very, very much. This was wonderful. My wife, Ann, could not attend because she's on a Zoom training mission with Longwood Gardens that started at 10 o'clock. So I thank the folks that have also set this up for being recorded so that she can look at it later on. The only thing I did want to offer was, that little saying for the naming of the planets in order. My very eccentric mother just served us 9 pickles. Well, since they got rid of planet, that left off the pickles. And so I came up with an alternative. My very eccentric mother just served us nutmeg.
That's pretty good. I can also say that you could, I hadn't thought of this, but you could change pickles to gherkins, which are dwarf pickles, I think. So then it would fit in very nicely.
That works good, yes.
We may have to rename Pluto to something that starts with G.
Quick question. I was wondering about Venus. You said the temperature of Venus is what, 800 Fahrenheit on the surface, but the rotation rate of Venus is like 300 plus days. So what about the side that faces this, that doesn't face the sun? Does that get cold? And why wouldn't you get dry ice or carbon dioxide in a liquid form? Certainly the pressure is high enough to do that. I was just curious about that.
That's a really good question. And whether you have memorized the rotational periods of the planets or just looked it up, I don't know. But Venus is a really interesting situation. There are 2 major motions we're all familiar with. We revolve around the sun. That's the period, rotation or revolutionary period, if you will, or 1 revolution. And we rotate on our axis, and that's a different thing. And we know what the Earth's is. In terms of Earth days, or in terms of actually Venus days, Venus is very unique. It rotates so slowly compared to its path around the sun that it very slowly changes its face towards the sun, which I believe, and this isn't something I've read, it's just something that seems to make sense. Those billions of years ago, when the carbon dioxide was building up for whatever reasons, and the envelope around it was getting thicker and it was rotating ever more slowly, imagine just how much heat could build up when for months at a time your face was facing it and the greenhouse had thicker and thicker glass and got hotter and hotter. With the combination of, if you will, the thick greenhouse glass and the slow rotation, slowly but surely the thermal inertia kicked in to where the envelope didn't actually change much when it was turned away from the sun, even though it was for a long period of months as well. It was just a greenhouse that kept that heat in, and the next time it faced the sun, more heat built up and it got hotter and hotter, such that there's no part of it that has anything above, I'm sorry, even approaching the boiling point of water. I mean, 862 degrees, I guess, is the temperature. Whether or not it has much excursion up and down as you go around the day-night cycle, which, like I say, is not much shorter than the period of rotation around the sun. So I don't actually know what the excursion is, but I don't think it's very far away from the center temperature there. That's a good question. I'm going to look it up after we're done here. So Ted and Dave, as I said, I do have another, 15 or 20 minutes if anybody's interested, but I respect your time limits. So being a retired guy, and many of you folks are as well, I don't think about that as much. But I can stick around if anybody wants me to, or just say I've really enjoyed this. It's been great, and they've been really good questions.
John,
Dave, your call, Dave.
John,
Yes.
this is Gene Moore. I have a technical question. I don't understand. How do you determine how many billions of years a solar system or planet was developed?
It's that's way out of my league. I don't know if I should be, but I've tended to believe what the astrophysicists and cosmologists have come up with as what I will admit are their theories, okay? For example, we understand very well it was in the first 5 minutes after the Big Bang. And the Big Bang, you may or may not know, is what scientists believe to be the initial introduction into space as we know it. All the material that ever will exist, okay? That's obviously not something that we know for sure, but that we do know with the way that physics has developed its understanding of clues and tested them whenever they could with actual observations, that in the first 5 minutes after the Big Bang, the first element formed, which took, you know, the better part of a second to form because it wasn't there initially, was hydrogen, which is, you know, simply one proton and maybe one or more neutrons in the nucleus and one electron. In the first 5 minutes, all of the helium ever produced was produced too by a combination of hydrogen atoms, and it makes up 25% of the 100% of the matter that existed in those 5 minutes. 75% of it was hydrogen, 25% of it was helium. I'm telling you things that many scientists have developed through the decades and tested with always peer-reviewed. I mean, there's nothing a scientist likes to do more than, one, be skeptical of somebody else's findings or theory, and two, prove them either right or wrong with more observations. So the scientists have come up with the model of what's happened, and the number of billion years, frankly, I can address that a little bit simply by saying we're going to show this and prove it even more with the engineering that's gone into the instruments on the James Webb Space Telescope. And as I say that, I'll point out that we understand very well how the electromagnetic spectrum works, and we understand that as space expands, as the universe has expanded, the source radiation, say in the ultraviolet from a star that's lit up, will be stretched. And as it stretches, it will be what's called red-shifted, which means moved to longer wavelengths. As you can picture the universe allowing the wavelengths that are already traveling across it to be stretched towards the red. That's what redshift means. And in order to look beyond ultraviolet, which comes next to the visible and then next to the infrared, we need detectors that can look there. And the James Webb is, by design, carrying detectors that can look at red shifts that will indicate times called look-back times all the way back to about the first 200 million years after the Big Bang. We've already, with Hubble, looked back, and this isn't theory. This is actually an understanding of science and detection and spectra and so on. We've already looked back about 13.4 billion years of redshift with Hubble. Its detectors can't look any further into the infrared, but James Webb by design will. And it'll allow us to look back to the time that these theories tell us will be when the first stars lit up. And by that, I mean enough hydrogen and helium got together in a cloud that under gravity compressed down and heated up to start thermonuclear fusion, which was a Nobel Prize winning finding of Hans Bethe back in the 30s. And I mean, this isn't theory, this is real, this is known things. And so we understand how stars are formed, and we're hoping to see literally some of the first stars with James Webb. And it will be focused, with all of our fingers crossed, properly, we hope, by about June, and we'll start to see the first images from it this summer. But it was designed to look back across those billions of years. What happened in the first, minutes and the first couple 100 million years? We have plenty of observations of things like the cosmic microwave background. And again, microwave indicated as being redshift all the way to the long waves, which are called microwaves, at the time that that would have taken place, which is well before the 300 million years after the Big Bang that we're now looking. And that was yet another Nobel Prize for some Bell Lab scientists back in the 60s, Penzias and Wilson, who discovered what had been a theory. But again, the process is always think about what you're going to look for next based on what you know. Think about what it might be, design an instrument, go have some experiments to look for it, see if you confirm it. That's happened countless times, especially in the last 100 years or so. And I'd have to say, especially in certain branches of cosmology and astrophysics, since Hubble started working in 1993. I mean, it's been perhaps the most valuable machine for advancing physics, certainly ever built. And James Webb hopefully will do the same thing again. We've had a revolution of understanding in only about 20 years, just as we've had a revolution in the roughly 3 decades of all those down-looking Earth satellites in understanding the atmospheric changes that are causing global warming.
John, I think you've got some fascinating information for us today, which is very much appreciated. And you mentioned you have some follow-on, more presentation that goes with, augments this presentation. I think we want to do that at another time so that those folks that have had to drop off, some have different calendar commitments, and we've lost about half a dozen or so. I think it would be beneficial if you would be so kind to come back and talk to us one time again with the rest of the presentation that you have. And maybe, if I could ask, augment that with what we do know from the James Webb as to how that continues the story.
Okay, I will be very happy to do that, and we can talk offline about exactly. I'll sort of outline what it would be and let you and Dave know, and we can talk about that.
Yeah, work with Dave Walter on that one. He's
Okay.
he's the program director on it. I'm the technologist and just poke my nose in once in a while on other things.
Okay, be happy
Dave?
to.
Yeah, John, you seem to have about 3 or 4 topics that we can use. So going forward for the fall and beyond, we'll be sure to get in touch with you. Before we all leave, I just want to mention next week's speaker is Malcolm Johnstone. We've heard him before. He's going to be speaking on art, architecture, and artisans and how they shape the Westchester community. So that should be very interesting. So we'll see you all next week.
And John, a big thank you so much.
Well, I have to tell you, you guys have been a great audience. I really appreciate it. And I hope I didn't undersell NASA there, but that's my job, is to sell them. All right, take care, everybody.
Well,
thank you.
Bye-bye.
Thank you.